Today, speakers are PhD candidates from diverse institutions and backgrounds, all united by a shared passion for leveraging geospatial tools to address pressing environmental issues, including the health impacts of hurricanes. So let me take a moment to introduce our distinguished speakers, each bringing unique perspectives and expertise to the table. Our first speaker, Bailey Maggers, is a PhD candidate in environmental engineering sciences from the University of Florida. He's a member of Dr. Antarpreet Jutla's GeoHealth and Hydrology laboratory. His research and career focus are at the intersection of climate and health, looking to develop tools for mitigation of diseases. Our second speaker, Margaret Larmore, is also a PhD candidate in geospatial analytics at North Carolina State University and is a member of the Urban Systems Lab in the Center for Geospatial Analytics. Margaret studies the environmental impacts of regional and land change, focusing on how land use regulations and flood management policies affect historical and projected human land use. Our third and final speaker, Kyla Drewry, is a PhD candidate in civil and environmental engineering at Northeastern University in Boston, Massachusetts, and is a member of the Well Water Lab. Her research bridges environmental engineering and public engagement to support disaster-affected communities by focusing on private well water quality, disaster response, and community science. So with that being said, without further ado, let's get started. Bailey, you may share your screen.
Thank you so much. All right. All right, thank you everyone for being with us here today. So today I'm going to present a lot about how remote sensing and Earth observation data sets can be used to develop predictive intelligence for infectious diseases. Particularly in the US, we are looking at Vibrios, and I will talk a lot more about the threats that they pose to human health and all those kind of things. So the first thing that I want to talk about is how climate and environmental variability impacts waterborne pathogens, how they emerge in the environment, how they are distributed, and when we can sort of see outbreaks of these diseases. So on the right, there's a figure that we've created that compiles all of the known knowledge about several waterborne diseases and the optimal conditions for temperature, pH, and salinity for those pathogens. And as you can see, depending on the pathogen that we're looking at, different conditions favor their growth. But for most, a combination of high temperatures and a certain salinity profile are conducive to optimal growth. For the three on the right, Vibrio cholerae, Vibrio parahemolyticus, and Vibrio vulnificus, these are some of the species that we're going to be talking about today. And they are emergence and distribution in the environment are heavily influenced by periods of high temperatures and rainfall that contribute to pH changes and changes in the salinity profile where they're found globally. So during Hurricane Ian, which is a few years ago, there was a big outpour from the media of these articles about flesh-eating bacteria and cases that were found along the coast of Florida. And flesh-eating bacteria is obviously very attention-grabbing and very, it's a headline that people are going to want to look into. But what's actually, occurring or what was reported during the hurricane were cases of vibriosis from Vibrio species. So vibriosis is an infection caused by either the consumption of contaminated raw seafood, which contain the bacterium, or, which is more likely during a hurricane, direct contact with a open wound with water containing the pathogenic Vibrio species. This is more likely during a hurricane because of storm surge, increased temperatures in the ocean waters or the estuary waters, as well as people that are in evacuation areas that aren't able to leave, getting injured, and those kind of things. But for Vibrio species, they are actually found in almost all riverine, estuarine, and coastal environments globally, as well as some freshwater ecosystems, depending on the ionic content of the water, where generally they prefer a more moderate salinity profile. Additionally, Vibrio species are ecologically significant bacterium. So to avoid cases of vibriosis or other infections from these bacteria, it's not feasible for us to eliminate the bacteria from the environment. We'll have to mitigate the disease instead and try and predict when and where these things will happen. So these two graphics kind of give you an idea of how Vibrio species are distributed throughout the United States, and what species are most prevalent in certain areas. So typically around the Southeast region, we see more of Vibrio parahemolyticus, Vibrio alginolyticus, and Vibrio vulnificus as the primary species that we're concerned about. Typically, Vibrio vulnificus is the one that we are the most concerned about. It is generally considered the most lethal of the Vibrio species in humans, where about 20% of cases can actually be fatal, particularly those that are caused by the direct wound infections. One thing that we can see here is that since 1990, so over the last 30 years or so, the number of vibriosis cases that have been reported in the eastern United States has increased dramatically, almost fivefold, going from a little bit less than 100 cases in 1990 all the way up to close to 500 today. And the three species that are being reported much more so than they were before are those three that I mentioned before: parahemolyticus, alginolyticus, and vulnificus. And I'm going to show you an image of what an infection looks like. If you don't want to see that, just look away for like 5-10 seconds. But here's what it looks like. These open wounds will become infected with the bacteria, and they will cause these skin lesions. And they are also primarily found in, the bacteria can be found in oysters, which is why that's shown there. So if you're eating raw oysters or some other raw seafood during certain times of year, particularly the summer, it might be something to be aware of and try to avoid. One thing that we know very well about Vibrio species is that environmental and climate factors play a significant role in their emergence and distribution in the environment. Specifically, sea surface temperatures, precipitation, flooding, coastal salinity, which I kind of mentioned earlier, but also dissolved organic matter content, chlorophyll, phytoplankton, and zooplankton concentrations. So those kind of drive the microbiological communities that are in the water sources, and can increased numbers of them can increase the likelihood that we'll see Vibrio species there. But all of these factors have been observed using, Earth observation satellites, remote sensing data, or reanalysis data sets, and compared with the either the sampling of Vibrios in the environment or reported cases to develop this connection. So talking about Hurricane Helene specifically, there were 38 cases of Vibrio vulnificus infections reported following the hurricane, with the two most impacted counties being Pinellas County and Hillsborough County. So as I mentioned, Vibrio vulnificus infections are fatal in about 20% of individuals, and about 50% of them result in primary septicemia, otherwise known as sepsis. And the reason why hurricanes are such a concern, kind of like I mentioned earlier, is that the warm waters and storm surge in coastal areas combine to create these optimal growth conditions for proliferation of the bacteria. And of course, the threat to humans, where they don't have access to normal medical means to kind of prevent the infections or to seek help after they've been injured or something like that, kind of creates the perfect storm for these outbreaks to occur. So what we want to do is, we know that there are several environmental parameters associated with Vibrios. We know that it is not something that can be, ecologically treated, where we can eliminate this bacteria from the environment. So what can we do to mitigate vibriosis in our ecosystem, or in our public health sphere? How can we limit the impact that it has? So what we are really concerned about is prediction and predictability of outbreaks. So on the left is a scenario in which we are able to, identify when an outbreak is going to happen in advance and intervene early to create a much smaller outbreak than would have otherwise been reported. However, what most public health agencies do now is they respond to the outbreak at its worst point, which does help relieve some of the tension caused by the disease. But realistically, there's a much better way to allocate resources if we know beforehand when an outbreak might happen. Particularly with hurricanes, this is important because obviously we can tell people to, evacuate and all these things, and the dangers of that. But another key issue is communication of risk of, touching and being in contact with storm surge water or any kind of flood waters, not just for Vibrio species, but other waterborne pathogens as well. And so identifying the areas that are most at risk of this and most at risk of the Vibrio actually being in those waters is really essential to mitigation and intervention efforts. So I'm sure, I mean, we're gonna hear about a lot today because it's all about geospatial tools, but just in case you're not familiar, remote sensing is one of the primary ways that we get this data set for environmental parameters associated with Vibrio species. And obviously the NASA and NOAA Earth observation satellites are primarily where we receive most of our data sets, but also from other reanalysis products uh, that are in combination with those Earth observation satellites. So a combination of in situ data as well to kind of move forward this research. So one area that our group has been working on for the last like 60 years or so at this point, in combination with not just the engineering departments that I'm associated with, but also the microbiological departments at University of Maryland. There's been a lot of research done on Vibrio cholerae, which is better known as the causative agent of cholera, which is a diarrheal disease that is often found in areas where water and sanitation infrastructure is not as readily available. And it causes, millions of infections every year, particularly in those developing regions of the world. And the primary research that's gone on for Vibrio cholerae is something that we can transfer to Vibrio species other than Vibrio cholerae. So starting back in the 60s, there was efforts to kind of show in laboratory conditions the environmental conditions that influence the proliferation of the bacteria and establishing how much of the bacteria is actually needed to cause an infection, those kind of things, and culturing the bacteria or finding viable but non-culturable states. Additionally, going into the 90s, that's when the field campaign started happening, and we started to do these outside of the laboratory in the actual environment where we can take these readings of temperature, precipitation, salinity, and other ecological parameters to identify where and when these bacteria are most prevalent based on the environmental conditions. And then in the 2000s, as Earth observation data become more prevalent, the first studies start being published about looking at sea surface temperature and chlorophyll or sea surface height in association with cholera outbreaks in the Indus River Basin, like Bangladesh and those kind of areas of the world. And eventually, as we keep progressing through these studies, we have developed a real-time prediction of cholera and using Earth observation data as the primary input for those models to predict when and where cholera will occur in different regions of the world. So this is an overview of our cholera hypothesis that's been developed from using Earth observation data and cholera incidence data in many regions of the world. So we have basically identified that a cholera outbreak is much more likely to occur when above average air temperatures followed by a period of above average precipitation in areas where water insecurity is an issue is the perfect conditions for a high risk of cholera outbreak. And we have integrated this hypothesis into our UF weighted raster algorithm, which is just the patented term for what we call our cholera risk model. So this risk model obviously integrates the climate data, so like temperature and precipitation, and the wash infrastructure data, which has data on drinking water access and sanitation access, but it also can include things like population density and socioeconomic data if we have it available, flood data or any other natural disaster data that can be incorporated in there, as well as the epidemic growth curves to produce in the bottom right a 1 by 1 kilometer risk map showing areas for the next 4 weeks that we believe to be at high risk of cholera outbreak or low risk of cholera outbreak. We have tested this hypothesis and this model in several areas of the world, including in Nepal following the earthquake in 2015, in Haiti following Hurricane Matthew, and I believe in 2016 or 2017, and more recently in Yemen, where we were actually able to get access to epidemiological data sets and compare our model results over a 3-year period with the actual reported cases there, and identify that our model is able to predict cholera cases with about 70% accuracy compared to the actual reporting numbers. And so now we've moved on to publishing a lot of our maps online. So we have a Vibrio prediction hub through the ArcGIS dashboard software that kind of hosts all our data for different countries, where people can go on there. They can request certain analyses for different countries or see just like what we published currently. And it has all of those risk maps on there if you're interested in checking that out. However, when we look at models for vibriosis and other vibrios in the United States, there's significantly less progress on determining risk of especially Vibrio vulnificus along the eastern United States and towards the Gulf area as well. One of the most notable models is the NCOS model for Vibrio vulnificus occurrence in the Chesapeake Bay Area, as well as people have been able to use the ECDC model for a daily suitability index. However, the model is more calibrated for the regions of Europe where Vibrios occur. So it's not exactly a great one-to-one prediction model for us. And so kind of our goal is to leverage the advances that have been made in genomic sequencing and microbiological sampling, along with advances in remote sensing technology to, observe the environmental parameters associated with Vibrio species and be able to make informed decisions about when and where these outbreaks are most likely. So on the right is kind of an example of how we might use PACE data, which is one of the newest satellites that's been launched for chlorophyll and for other, as the data products become available, it will be available for phytoplankton products as well. And so that's kind of the future. And so in summary, all these new technologies and things have created, a real opportunity for us to have real-time monitoring of the environment and how Vibrio species will become emerge in those conditions. And hurricanes, are very much in certain conditions going to facilitate that interaction of human and pathogens. And we can use the lesson learned from our cholera model and our Vibrio cholerae projects to, help in mitigation for projects in the US. And with the, threat to human health that vibriosis presents, there's a huge opportunity for us to, design these interventions and really improve the quality of human and public health access that we give people during hurricanes. And so that's it. And so if you have any questions, my email's there, and I'd be happy to answer them if we don't get to them after this presentation here. So.
Yes, thank you, Bailey. That was a great presentation. And I'd also like to remind people, the new attendees, feel free to type in your questions in the Q&A, or you could wait at the end of the seminar and ask them yourself and raise your hand and I'll unmute you. So thank you again, Bailey. Now next, Margaret, you can go ahead and share your screen.
Hi, thank you, Melisha, for the introduction and Bailey for starting us off today. Just a reminder, my name is Margaret Larimore, and I'm a PhD candidate in geospatial analytics at North Carolina State University. Through this presentation today, I will be sharing research my lab recently published, where we used geospatial methods to explore one flood management policy used in the United States and see how it influences development patterns locally and across the nation. Now, to tell this story of US flood management, I want to start today in my hometown. Asheville, North Carolina is nestled in the beautiful Appalachian Mountains of the western portion of North Carolina. And ever since I moved away nearly 9 years ago, whenever I mention my hometown, 9 out of 10 times, folks respond excitedly with stories of their last trip to Asheville. Some folks will recount our wonderful downtown filled with all of our local vendors, a couple of chocolate factories, and more than a few local breweries. Others will mention taking meandering drives along our Blue Ridge Parkway. And others still may be lovers of nature and talk of taking hikes and taking in views of our gorgeous Blue Ridge Mountains. But recently, those stories have changed. In late September of 2024, Asheville and the surrounding area experienced historic flooding, landslides, and widespread devastation as a result of Hurricane Helene. In the aftermath of Helene, folks, including my family and friends, were left with countless questions. Beyond just the how did this happen and the how are you doing, folks were wondering how so much flooding occurred in areas they were led to believe had little or no flood risk. And these questions that were spreading among my families and friends reflect the same confusion and uncertainty that has faced countless communities affected by this and many other natural disasters that preceded it. Locals, politicians, scientists, journalists, all wondering why so many homes and businesses outside of the floodplain end up damaged. And through this project, we aim to provide context to begin answering these questions. Now, specifically, we explore how the designation and communication of high-risk flood zones via floodplain designation shapes our development patterns. To answer our question of how communicated flood risk shapes development patterns, we developed a methodology divided into 3 main stages. Starting with our first stage, we wanted to better understand how flood risk designation operates in the United States. For this, we turned to the U.S. Federal Emergency Management Agency, or FEMA's, regulatory 100-year floodplain. Now, essentially, the 100-year floodplain indicates areas with a 1% chance of flooding in any given year. That is, in areas that are shown in blue on this map, there is a 1 in 100 chance of flooding every year. And homes and businesses inside of the floodplain are subjected to stricter building requirements and are required to purchase flood insurance given their heightened risk. On the other hand, in areas that are shown in gray on this map are outside of the floodplain and are considered to have minimal risk and are not subjected to the same regulations as areas that are inside the floodplain. Now, today, rather than touching on the specific accuracies or inaccuracies of the FEMA floodplain, I want to address the communicated risk. And with this, there's one critical component of our floodplain designation that I want to make clear, and that is there is a binary characterization of risk. If you're within the floodplain, your risk is considered significant. If you're one step outside of the floodplain, your risk is communicated to be minimal, despite the reality that flood risk does not abruptly stop at the floodplain's edge. So given this binary characterization, we were wondering what happens in terms of development in that space just outside of the floodplain. To understand this, we generated 10 250-meter concentric distance zones going from the edge of the floodplain to 2 kilometers outside of the floodplain. These zones are shown here on the slide, with areas in darker shades of blue being closer to the floodplain and areas further away being shown in those lighter shades of blue. Now, for your reference, 250 meters is roughly the size of 1 or 2 city blocks. And I'll be returning to the slide in a few moments to talk about it in more depth. So now that we understand where and what the floodplain is, I want to move on to the second stage of our workflow, aiming to understand our past and future development patterns and where development is occurring in terms of its proximity to the floodplain. To predict future development patterns, we use the Futures Urban Growth Model to predict likely development patterns out to 2060. Now, I'm going to spare you the details of our model, but I do have a QR code here on the slide where you can find out more. And I'm also happy to answer any of the questions you can put in the chat or talk about it after the presentation during the Q&A portion. So returning to our map showing the proximity of proximity to floodplain boundaries, we can overlay development patterns as of 2019, shown here in orange, to begin to examine visually where development is in relation to the floodplain. Now, of course, at this scale, what we're mostly seeing in orange are our larger cities and metropolitan areas, but I'm going to be digging in more into what all of this really means in just a moment. We can also predict development out to 2060 and show where future development is likely to take place. And here on this slide, I'm showing the probability of development with the highest probability shown in the brightest shades of orange and the lowest probability in the whites and pale yellows. For this, we predicted a status quo development. So much of the development is occurring near or around the development you would have seen on the last slide. And again, at this scale, it's a little bit hard to tease out any clear findings. So I want to move on to the final part of our workflow so we can begin to see what this all really means. In the final stage of our project, we conducted a simple statistical analysis to explore how floodplain regulations relate to our development at the national, state, and local levels. Now I want to begin again with our national extent and return once more to our map illustrating the distance to floodplain boundaries. So here we see the floodplain again and those distances from floodplain boundaries. And I want to take a look at how our exposure, our distances to floodplain boundaries vary geographically across the United States. If you take a look at the southeastern portion of the United States, you're going to see a lot of shades of darker blue. And that's indicating that a lot of that land is falling quite near the floodplain boundaries. And if you look at Florida in particular, you see a very strong case of much of the land falling inside or just outside of the floodplain boundaries. However, if you take a look at the western portion of the United States, you'll see a very different story. one where much of the land is falling much further away from the floodplain and falling even 2 kilometers outside of the floodplain boundary. However, when we take a look at what all of this means in terms of development's distance to floodplain boundaries, we see a different story. One where development is consistently and disproportionately located near within 250 meters of the floodplain across the entire United States, regardless of what region we're talking about. And on this map, we're showing each county in the United States colorized by the zone with the greatest proportion of developed land. Counties with greater proportions of development in zones closest to the floodplain are shown in our darker shades of blue, and those with a greater proportion of development further from the floodplain are shown in our lighter shades of blue. As you can see, most of the counties have development predominantly near the floodplain, shown in those darker shades of blue. We can also break this down graphically and take a look at where development is occurring across the entire United States. And what we see is that the majority of developed land is again within those first 250 meters near the floodplain boundaries, with 24% of all developed land in the United States located within that first 250 meters outside of the floodplain. In this graph, we're showing total developed land in the United States in 2001, 2019, and projected out to 2060. And in each of these cases, we do see the same peak in development with that in that first 250 meters outside of the floodplain. We can also take a look at what these trends look like broken down per state. And so that's what I'm showing here on this slide, where we can see developed land area by zone for our 2019 development across every state in the United States. And across every single state, we see the same trend that we saw nationally, where the highest levels of development are found in that first 250 meters just beyond the floodplain boundary. You can see this trend nicely in North Carolina, which I have highlighted in orange on the slide there, where you can see that peak at 250 meters with a slow decline down to areas 2 kilometers outside of the floodplain. Speaking of North Carolina, I want to return to where I grew up and where we started this presentation, back to Hurricane Helene and Asheville, and see what all of this looks like on a local level. So here we are again in the beautiful mountains of North Carolina, and we can add our 100-year floodplain on top to see where it is occurring in this environment. You can see a large section of the floodplain down at the bottom part of the screen, with it spreading up into the top and right sides of our slide. We can also add those 250-meter buffers on top to see where our land is falling in regards to its distance from those floodplain boundaries. And again, on this slide, we're showing darker shades of blue corresponding to areas that are closer to the floodplain boundaries. Now, once again, we can add development on top and see where it is in regards to our floodplain boundaries. And as what we're seeing here is echoing what we saw nationally and statewide, where much of the development is occurring right on the edge in the first 250 meters to 500 meters away from the floodplain boundaries. So what we're seeing here in Asheville and what we saw across all of North Carolina and across all of the United States is this trend where development is consistently and disproportionately concentrating just outside of the edge of the floodplain boundaries. So what does all of this actually mean when taken together? Well, our research is suggesting that the floodplain, and in particular its binary characterization of risk, creates a false perception that homes and businesses just outside of the floodplain are fully safe from risk. There is not a wall separating land that is inside the floodplain from land that is not, but the risk is communicated as though that is the case. People love water and beautiful scenery, and so often we're pulled towards these beautiful regions that also tend to have higher flood risk. And when risk, which is not binary, is communicated as though it is, there is an unintentional incentive placed on the land just beyond the floodplain. This situation, where an effort to reduce flood risk paradoxically and unintentionally increases exposure, is called the safe development paradox. That is what our research suggests is occurring with the US federal 100-year floodplain. Well-intentioned flood designations intended to reduce flood exposure unintentionally incentivize the land just outside of the floodplain, despite the reality that flood risk extends beyond the boundaries. This safe development paradox shapes our built environment in Asheville and across all of North Carolina and the rest of the United States, and is at least one part of the answer to our questions, wondering why so many homes and businesses are affected by flooding from natural disasters. This research is a wonderful example showing why geospatial methods are so important and so uniquely suited to address our complex socio-environmental issues. Thank you so much for your time. I'll be happy to answer any of your questions in the chat or during the Q&A portion. I'd also like to thank co-authors on this research, including our lead author, Georgina Sanchez, along with the funders of this project, including the Southeast Climate Adaptation Science Center and the U.S. Department of Agriculture. Thank you.
Thank you so much, Margaret. Now we can move on to our third and last speaker, Kyla. You could please share your screen.
Hi, thanks so much for the introduction. Okay. Good afternoon. Thank you so much for having me, and really interesting talks from the first two presenters. I would love to talk to both of you guys after. My name is Kyla Drewry. I'm a PhD candidate at Northeastern University in Boston, and today I'm going to be talking about our team's development of a decision support system to aid environmental health department response after Hurricane Helene. As mentioned in the introduction, our research group focuses a lot on private wells. So private wells provide drinking water to about 45 million Americans and an estimated 3 million North Carolinians. These are unregulated drinking water sources that are not protected by the EPA. So the responsibility to test and treat and monitor your drinking water quality falls on the responsibility of the owner. When flooding events like Hurricane Helene occur, contaminants in the floodwaters can infiltrate into the groundwater and get pumped directly into homes. So microbial contamination as total coliform or E. coli, which pose health risks, can be unknowingly in these systems. So in comes our team, the Well Water Lab. We are a combination of academics, working with the North Carolina Department of Health and Human Services, as well as nonprofits like the River Keepers of North Carolina, the North Carolina Groundwater Association, and a bunch of individual counties. And we're a NASA-funded group that's been working together over many, many years to try to put together a well water surveillance and response system. So essentially what we're doing here is taking publicly available data and data sets, looking at private well tests from North Carolina Department of Health and Human Services, and combining that with some of our known groundwater data from the North Carolina Department of Environmental Quality. And then we're taking some satellite and remotely sensed data products, as well as some other publicly available data to look at trends in drought, flooding, land cover. And what we really want to do is take all of these available data and put them into a portal so that local health departments can use these geospatial tools to inform their decision making. There are so many amazing products out there, but implementing them in a combined way is often really challenging. And so our team's job is to try to lift up a surveillance and response system so that North Carolina on-site water protection can use this. And our four main goals are enhancing monitoring and sampling efforts, improving targeted response after disasters, targeted outreach in preparation of a hazard, and in general, spatiotemporal mapping of well water contaminants to kind of understand what the risks are to these private well users. And so now I'm going to go into a little bit about the specific work that we did after Hurricane Helene, providing real-time data for decision-making by health departments. So as we all know, Hurricane Helene made impact on Western North Carolina in September of last year. And in yellow, you could see the outline of counties that were eligible for FEMA assistance following the storm. And it's also overlaid there with the density of private wells. So as you could see, in some of those rural, more mountainous areas of Western North Carolina, we see really high density of private wells. And given the fact that this flooding event happened in Western North Carolina, where a lot of people didn't expect that they had flood risks, this was a really dangerous situation. So kind of a timeline of how we reached out to our collaborators at North Carolina Department of Health and Human Services and put together this decision support system. On Friday, September 27th, while the storm was still going on, we reached out and started to talk about what were their needs and kind of develop a plan. So over the years that we've been collaborating with DHHS, they have given us so much help with data and understanding like local dynamics of the communities that we're working in. They've helped us with papers and posters. And so this was really an opportunity for us to give back to them in a moment of crises. So this is the overall timeline. And then I'm just going to kind of walk through step by step how we went from initially meeting with them to disseminating our portal. So on Friday, we reached out to DHHS and asked how we could be of assistance. It was kind of a very preliminary meeting saying, what's going on? What do you guys need? At this time, they were still in search and rescue mode and things were very chaotic. And so we just kind of said, let us know how and when it's appropriate to help. In the meantime, we were looking at some of the flooding trends, building on some of our prior work. So Margaret just talked a lot about FEMA's 100-year flood hazard area, which is derived from hydrologic and hydraulic models and identifies locations that have a 1% chance of flooding in any given year. There are known limitations to this model. First of all, in the binary approach that Margaret was mentioning, and then also in the fact that these maps are not storm specific, and they just highlight a 1% chance of flooding in any given year, kind of separate from what a storm impact may be. Our team has been working towards gaining more accurate flood estimates. And one way that we've been doing that is leveraging geospatial data from National Weather Model to create the height above nearest drainage derived extents, which I'm going to be referring to as HAND for the rest of the presentation. This model incorporates reach average relationships between water depth and river discharge based on Manning's equation. And so if you're not really great at fluid mechanics, or you're kind of like, what is she talking about? Here's a little breakdown about how we get a HAND estimate. So if we have a point up there on a hill, and we're wondering what is the flow rate Q through a river that's required for the floodwaters to reach at that height. So HAND takes gauge observations from rivers and estimates what that height needs to be from the flow rate. But a main challenge that we have with HAND is that we often don't know what the basin of a river looks like. So there's the area parameter there that you need. And so if the bottom of a river is triangular versus rectangular, that makes a pretty big difference. And so while HAND is really cool in that you can provide storm-specific rapid flood mapping models, there definitely requires some calibration. And so members of our team have been working to optimize HAND in North Carolina to adjust it to be closer to the FEMA 100-year floodplain and represent flooding more widely. And so our work over the years optimizing HAND led us to be able to provide local health departments with a near real-time flood map. So that on the right there is a Jupyter notebook. And so basically we have it to a point now where you have this hydrologic region outlined in red. You can put in your region numbers, set a date range for the event, and it will automatically pull some of that stream gauge data, run the HAND calibration, and output a map. So this is an example of a HAND map that we generated following Tropical Storm Debby, which hit the coastal part of North Carolina back in August. So this was really a chance for us to launch and pilot test our hand extents. And we were able to validate where we estimated there was flooding by conducting on the ground well water tests. So we provided over 300 well water testing kits to private well users in North Carolina, testing for total coliform and E. coli to see if floodwaters and bacteria had gotten into their systems. And our results was that Debby had minimal flooding impacts, and this kind of aligned with what we saw in the hand results, and that it was less than a 100-year storm. But it really gave us the chance to evaluate what went wrong and what went right. And we had thought to ourselves that this is a great experience to prepare for next hurricane season. But then 1 month later, Helene hit. And so we were prepared to develop a near real-time flood boundary. And that's what we did over the weekend. And we output this height above nearest drainage extents, showing areas that were likely flooded following Hurricane Helene. So we reported back to our collaborators at NCDHHS, and we said, we have this flooding extent. It's at a 10-meter resolution, and we were able to develop it within hours of the storm. They kind of said, well, areas that weren't just flooded, what did the rainfall look like? And so we pulled some data from NASA, iMerge GPM, and found precipitation totals at 10 by 10 kilometers grids. And this data was available 12 hours after the storm. So we were really working rapidly to try to put together data products that could be used to advise recovery efforts. That following Tuesday, we started to compile more data products, talking more with our collaborators. They saw the environmental conditions and they said, great, but what are the impacts on businesses, schools, relief centers? They wanted to know information about who was using wells and potential contamination sources in the area. So there was a lot of back and forth here talking about what kind of data products could be helpful and how we could leverage these flood maps and precipitation data to overlay with businesses to estimate impacts. And so here is just an example of private well estimates by census block. And you could see we have our hand boundary in dark blue running through there. And we could see areas that had both high private well usage and high amounts of flooding to try to target some of those testing resources like we used after Debby to areas that needed it after Helene. Like I was saying, we talked a lot about recovery priorities. So what areas can we provide data for that would be useful? Something that came back repeatedly was schools, businesses, restaurants. It's On-Site Water's job to get businesses up and running again after they're flooded. So determining if a restaurant was flooded or not is really important. The ability to visualize those impacted areas and zoom in on a map and actually see it was something that was reported would be really useful to help them prioritize the distribution of recovery resources and then inform emergency response funding requests. So to go to FEMA and say, we think we had these impacts. And so these are all the sources that we pulled other data products from. We used SafeGraph for businesses, estimated well use data from the EPA, known public water and sewer covered areas from NCDEQ. Also from NCDEQ, we found known sources of release of contaminants. So these included landfills, underground storage tanks, and septics and other things that could release contaminants into the environment. We also have U.S. Census demographic data and land parcel information. So on Thursday, October 3rd, we launched an ArcGIS experience, which had all of this publicly available data aggregated and compiled for users to use. This was kind of our first go at releasing data. And we just launched it to the local health departments within the disaster impacted counties and then allowed feedback on the resources and products. This is kind of how the whole dashboard looked. So you're able to select individually by county, and then there's all of the different drop downs there, and a legend. But we kind of got some feedback about how to optimize the user interface. So we took that single dashboard, and we embedded it into an ArcGIS hub. And within the hub is kind of like a full website, and I'll share the link at the end, but you're able to see not only the data, but also resources and announcements from NCDHHS, videos on what to do if you have problems with your system. And it kind of became a landing page for recovery data of all kinds. And so this is kind of what it looks like. The link is up here, and if you follow that bit.ly link down below as well, that's an option. So this is some of our estimated impacts. So we took all of the data that was in that dashboard and started to come up with summaries that we could quickly report to our collaborators, because at the local level, it was great to kind of look around and see what areas were flooded. But at the state level, we were getting requests to say, okay, we need to go to the governor and say what we think the impacts were to restaurants, to private wells. And so we broke this down by different types of community locations, what the total population was, what were in our hand estimated flooded areas. And then we also did 100-meter buffer to say what was in 100 meters of estimated flooded areas, because again, flooding risk is not binary. We broke this down by county as well and estimated the number of private wells that were likely flooded. As our conversations continued, we got requests from the head of on-site water protection at DHHS to kind of turn these estimates into reports. And this kind of gave us bookends about what to think about to do for recovery efforts. So here we have the number of wells and number of well users within each of the impacted areas, and wells that fell within our estimated flooding extents. So we estimated that there was likely somewhere between 20,000 to 80,000 wells that may have been impacted by flooding, which was a really wide range. But to have that number less than a week after the storm was really crucial and important. We did the same thing looking at estimated known sources of release of contaminants and businesses and organizations. And we were kind of pumping out these reports for all counties, and then also by individual county. So this is a report that we generated just for Buncombe County, where Asheville is located, at rates kind of as fast as we could. Yeah, you could see the date on this is October 8th. We were putting this together. So we found that while engagement in our portal was pretty widespread, you could see a large hub of users were from Asheville and throughout North Carolina. And it was used pretty rapidly within the first 2 weeks. The feedback that we got from health departments was that some of those generated reports were quicker and more accessible, while the portal kind of served as a way to look at highly localized impacts. This is another figure showing the engagement of our portal over time. You could see that in the first couple of weeks following the storm, our engagement really peaked. And the number of new users was also pretty high. And as the weeks kind of went down, we saw some repeat users, but overall less engagement, which makes sense as they were kind of using it for immediate recovery advice. These are some of the other resources that were put into the dashboard. Our estimates ended up being used by DHHS in some of their press releases, and even the governor ended up using some of the estimates that we came up with to request money from FEMA. So it was a really neat example of how this data could be used in real time for decision making by states. Again, some of this work was published in the New York Times, which I thought was really interesting. They referenced some of our estimates, especially because private wells are often a drinking water source that's overlooked. It was really nice to see this get some media coverage. So overall, lessons learned, we found that actionable data was less actionable than intelligence during the immediate response phase. So that's kind of going back to having those reports generated and sent out to officials was more helpful than giving them the whole database, because that was a little bit overwhelming for some local health departments who had limited GIS experience. But user-friendly analytics within the decision support system could be something we could do to enhance functionality and usability. So instead of users having to pull all of those calculations out to generate those reports on their own, if we could embed that in the dashboard, that would be something that would be great. Our hope is to increase targeted training of local health departments and emergency health staff prior to emergencies, so that we can empower local health departments with the skills, resources, and knowledge to recover. We also have a lot of ongoing collaborations. We've been developing videos, educational materials, well testing, sampling campaigns, and we're still constantly working on improving our data products, looking at resolution, time latency, accuracy, and user accessibility. This is like some of the videos that we were posted in collaboration with DHHS. And this was an effort when we went down to Asheville in October after the storm and built mock wellheads, which were used as educational tools to show residents what their system looks like, how to test their well, and how to disinfect it with chlorine bleach. So what's next? Continue listening. I really want to emphasize that this was an iterative process with our collaborators that's been going on for many years. And we have this overarching vision to empower local health departments with GIS-enabled tools. So we want to continue curating these data products to create a more user-friendly geodatabase. We're also working on surveys and interactive courses with local health departments. There's a well water symposium later this summer that our team is going to teach some GIS classes. Development of training modules, so understanding private well contamination after emergencies, and then actually going out in the field and testing private wells for these bacteria so that we can validate some of our products. So this is a co-design process. It's incredibly iterative, and Hurricane Helene was a really interesting pilot case that we got to be involved with and help and give back to our collaborators who have been helping us for so many years. So yeah, thank you. If anybody has any questions.